Named reactions and distinguishing tests in one shot. If you're new here, I'm Ashlin, second year student at NIT Calicut. Today we'll be revising the entire named reactions and distinguishing tests which are repeatedly tested in JEE mains. And without any further ado, let's start our video. We will begin with the Wurtz reaction, which is used to prepare alkanes from alkyl halides. You can see that when you are reacting it with sodium and dry ether, you will be getting hydrocarbons. And you should note that dry ether is used here because sodium reacts vigorously with other solvents like water, ROH, and acetone. And methane cannot be prepared in this Wurtz reaction because minimum is 2 carbon, and using two different alkyl halides will be getting different product, and the yield is bad, so you will be avoiding that. You can see the reaction mechanism over here. There will be radical forming and R radical will be combining to form RR. Then check out this question where you have two chlorine, and chlorine will be leaving and forming a radical over there, and intramolecular Wurtz reaction also will be happening. This is also possible. Please note this as well. Then we have Franklin reaction wherein you will be using zinc instead of sodium dry ether, and you'll be getting a similar product hydrocarbon over here as well. Next you have Fittig reaction wherein you will have aryl halides turning to diphenyls, and the reagent is same as Wurtz reaction with the sodium and dry ether. And then you have Wurtz Fittig reaction where mix of alkyl and aryl halides are turning to alkyl arine, that is one alkyl halide and aryl halide in the presence of sodium ether is giving this product. Then you have soda lime decarboxylation, which is used to prepare alkanes from carboxylic acid. You have carboxylic acid in the presence of sodium hydroxide and calcium oxide giving you RH. You should note that alkanes produced contain one carbon less than the carboxylic acid, and that CO2 is lost as carbon dioxide. That is why it is named decarboxylation. Next, you have coal-based electrolysis, which is also used to prepare alkanes from carboxylic acid. Here, you have aqueous solution of sodium or potassium salt of monocarboxylic acid, and the electrolysis gives alkane with the even number of carbon atoms at the anode. Here also two carbon alkane chain will be combining together to form an alkane. You will see that now. First, as this is an electrolyte, it will be forming CH3COO minus, and at the anode, oxidation takes place. I hope you saw the physical chemistry one-shot video also. In there, I discuss anox. Anode oxidation happens, and so oxidation is loss of electrons. So it loses electrons and forms radicals, and it further loses carbon dioxide and to form CH3 free radical. Then they will combine to form CH3CH3. This is what I meant when they form even number of carbon atoms at anode. And at cathode, you can see reduction happens, that is accepting of electron, and you can see hydrogen gas is released. And methane cannot be prepared over this because as you see there is two carbons coming together. Methane is CH4, which cannot be produced over here. Moving on, we have Lin-Las catalyst, which is used to prepare alkenes from alkynes by partial reduction. And this palladium carbon quinoline is a poison which is used because when we are using hydrogen directly without these poisons, it will be completely turning to alkane. To prevent that, we are using these, and this is Lin-Las catalyst, H2 in the presence of palladium or carbon or quinoline, and we'll be getting cis alkene in this. Note that. And next you have Birch reduction, wherein you will be using the reagent sodium in the presence of liquid ammonia. This also will be giving you alkene, but this gives you transalkene. Cis, you can see both hydrogen, both RR is in the same direction, but transalkene, you can see both hydrogen is in the opposite direction. I hope you got this. Next, we have test for unsaturation. Here we will be using Br2CCl4, and you can see that when there is saturation, that is in alkenes, this will be decolorizing the reddish brown to colorless. But in case of alkanes, there is no reaction and hence the color remains same. You should note that benzene, although it has pi electrons, it is delocalized and hence it does not go on addition reaction and it won't decolorize bromine water. Next up, you have oxidation of alkenes, and you have Bayer's reagent, which is alkaline cold dilute KMnO4. This alkene is turning to a vicinal diol, and the name is ethane 1,2-diol, and it is also known as glycol. You should note that. And this is also a test for unsaturation. because this reagent is purple in color, and on reaction it turns colorless. Next you have acidic KMnO4 or acidic A2Cr2O7. This what happens is alkenes is getting oxidized to ketones or carboxylic acid. In this case you see that it is getting oxidized to ketone. A trick is you can break that double bond alkene over there and insert oxygen on both sides. Similarly, this is converting to aldehyde first, and it is further getting oxidized to carboxylic acid. Next, you have ozonolysis of alkenes. Alkene plus O3 first gives you an ozonide intermediate, and then when you are using sink water, it will give an oxidized product. It will be an aldehyde or ketone. You can see the trick over there. You can break the double bond and insert oxygen in both sides, and you'll get the product. This works in most of the cases. You should note aldehydes are not oxidized further as in the previous case. Previously, we saw that when you are oxidizing using KMnO4, K2Cr2, so on, the aldehydes were oxidizing to carboxylic acid. But here, the addition of zinc dust prevents the further oxidation of aldehydes to carboxylic acid. Then you have ozonolysis of alkynes, wherein the final products are dicarbonyls. You can see ethane diol getting forming, and you should note this ozonolysis of alkynes in the absence of zinc. In the second step, you have zinc water, and if zinc water is not present, this converts to carboxylic acid. Next, we have tests for terminal alkynes. This is because of the acidic nature of the terminal hydrogen atom. They will be reacting with the Tollens reagent and ammoniacal cuprous chloride. In case of Tollens reagent, it will be forming white precipitate, and when you are putting with ammoniacal cuprous chloride, you will have some red precipitate. So this can be used as a test for terminal alkynes. Friedel-Crafts alkylation, you can see that you have RCl, anhydrous aluminum chloride, and this RCl, it gets converted to R plus electrophile when it is reacting with the anhydrous aluminum chloride. You can see the hydride shifts happening below. You can see an example. You have CH3, CH2, CH2Cl plus aluminum chloride. First, it will be forming a 1 degree carbocation when it is reacting with aluminum chloride. And then what happens is, as you know, 2 degree carbocation is more stabler than 1 degree carbocation. There is a hydride shift happening, and 2 degree carbocation is formed. And then this 2 degree carbocation goes and attacks the electron rich benzene, and then you will be getting this product. And speaking of acylation, you have acyl chloride over here instead of alkyl chloride, as in the case of alkylation. Here you have benzene, acyl chloride, and anhydrous aluminum chloride, and you will be getting a product like that. And the electrophile is RC double bond O plus. You will be seeing the mechanism now. The first step in the mechanism is to forming the electrophile. This is an electrophilic substitution reaction, and you can see that first step is the formation of electrophile. And when you are reacting the acyl chloride with the aluminum chloride, you will be getting the electrophile like that. And then now when the benzene, the electron rich benzene is attacking the electrophile, you will be getting the arenium ion. That is the second step. And now you have a hydrogen over there. To remove that, you need a base. And here the base is AlCl4 minus, and that will be removing the hydrogen from that, and you will get the final product as that. I hope you got this mechanism. And this is an electrophilic substitution reaction, mind that. Moving on, in haloalkanes and haloarenes, we will start with Finkelstein reaction, which is the preparation of alkyl iodides from any other alkyl halides. This is a halogen exchange reaction. The reagent is NaI, sodium iodide, and dry acetone. You'll be getting Rx. X is chlorine or bromine, which is getting converted to Ri and NaX. And over here, NaX is precipitated in dry acetone, which facilitates the forward reaction according to Le-Chatelier's principle. When the products are removed or it is consumed, then the reaction moves forward to maintain the equilibrium. That is what the Le-Chatelier's principle is telling. And this reaction is primarily for the preparation of alkyl iodides. Next, you have Schwarz reaction, which is for the preparation of alkyl fluorides. This is also an halogen exchange reaction. You can see, for an example, CH3Br. When you are reacting with AgF, it is converting to CH3F. And other reagents which can be used is SbF, CO2, silver, and mercury, Hg2F2. These are the reagents which can be used for this reaction. Next, we have preparation of haloarenes from benzene diazonium salt. We have three named reactions. First is Sandmeyer's reaction, wherein you are treating benzene diazonium salt to Cu2x2 and you're getting haloarene. And in Gattermann reaction, you are using copper powder instead of Cu2x2 along with HCl or HBr, and we are getting haloarene. In this, the yield in Sandmeyer reaction is found to be better than Gattermann reaction. Then we have Ball-Schiemann reaction, which is specifically for the creation of fluoroarenes, and we are using the reagent HbF4. And if you are wondering how benzene diazonium salt is prepared, this is how from aniline. When you are treating it with NaNO2 HCl in the temperature 273 to 278 Kelvin, you'll be getting benzene diazonium salt. In JEE mains or NEET, they can give this as first step, and then they can give the next step as Handmade, Caterman, or Bolshevin, anything. I hope you will be doing that. And you should note that due to the instability of the diazonium salt, it is not generally stored. It is used immediately after its preparation. Next, we have reactions with metals, and we already saw Wood's reaction and Franklin reaction. Now we'll be seeing the Grignard reagent. Grignard reagent preparation is done like this. An alkyl halide, when it is reacting with magnesium in the presence of dry ether, you will be getting RMgX, and RMgX is the Grignard reagent. In this, RMg bond is primarily covalent and MgX bond is predominantly ionic. And you can see the charges also, which is rich in electron and which is deficient in electron. You can see R is a little bit rich in electrons and Mg is deficient. And this Grignard reagent can act as nucleophile and bases. In nucleophile, it can undergo addition reactions and substitution reaction. We'll begin with Grignard reagent acting as nucleophile and its addition reactions. With aldehydes, these form alcohols. In case of formaldehyde, when we are reacting with Grignard reagent and in the second step with H plus H2O, you will be getting 1 degree alcohol, and with any other aldehyde, we will be getting 2 degree alcohol. We will be seeing the mechanism now so that you will get a more clear understanding. Now we have the aldehyde over there. Whenever there is something as electrophile, that is which is electron deficient, now we can see that carbon oxygen, that carbonyl bond, oxygen is more electronegative, so it pulls the electron towards itself and carbon becomes bit electron deficient. So what happens in this Grignard reagent, you can see R is a little bit electron rich. So this electron rich goes and attacks the carbon, which is electron deficient, and you will get a compound like that. And now this is the first step. The second step is when H plus comes and attacks and forms the final alcohol compound. H plus goes and attacks there and it goes there and you will get the alcohol. I hope you got this. Basically, there is a carbonyl bond wherein carbon is electron deficient and R in RMgX Grignard reagent is electron rich. It is going attacking there and you are getting the final compound. I hope you understood the mechanism. Next, in place of ketones, only different from the previous reagent is in the second step we'll be using NH4Cl aqueous, and this is used for the hydrolysis because it helps in avoiding the elimination reaction, and here you can see it is also forming alcohol. Next we have reaction with acyl halide. When acyl halide is reacting with Grignard reagent, so here we need 2 moles of Grignard reagent. Note that as well. And when you are checking the mechanism over here, you'll understand why 2 moles are required. The first mole, first when it is attacking over here, this is forming a ketone. And the second RMgX, it attacks the ketone and it forms the product. Here also you can see the same mechanism, like the carbon is electron deficient and R, which is electron rich, is going and attacking the carbon, and then the reaction is proceeding. Same thing. You can note this logic and apply this whenever Grignard reagent comes. Next, we have reaction with esters. Esters, when it is reacting with Grignard reagent, you can see that it is also forming alcohols. And cyanides, when they are reacting, they form ketones. And when CO2 is reacting, we'll be forming carboxylic acid. You can check out the mechanism for carbon dioxide. Even in carbon dioxide, we have carbon, which is little bit electron deficient, and this electron rich R is going and attacking there, and then we'll be getting a compound like this, and finally when you're hydrolyzing you will be getting carboxylic acid. Next we have nucleophilic substitution of Grignard reagent. Here you can see Rx, alkyl halide. This X is getting substituted into R1. This is regarded as the preparation of hydrocarbons as well. You can check out that. When it comes to epoxides, you can see that it is forming an alcohol over there. The O bond is breaking, and in the one side the R1 from R1 MgX is getting attached, and the other side hydrogen is getting attached. Next we'll be seeing Grignard as base. In this, when you are reacting Grignard reagent with any of these H2O, ROH, NH3, amines or H2S, you will be getting RH. It is the preparation of hydrocarbon. And when talking about terminal alkanes, this Grignard reagent goes and attacks and it forms hydrocarbons as well. So, Grignard as a base overall, it behaves as the preparatory step for hydrocarbons. It extracts out the hydrogen from other reactant and R from RMGBr. So, you are getting a hydrocarbon over there. I hope you got this. Moving on, in alcohol phenol ether, we'll start with the Lucas test, which is basically the preparation of haloalkanes from alcohol. This test is used to distinguish between 1 degree, 2 degree and 3 degree alcohols, and the reagent is concentrated HCl and anhydrous zinc chloride. Alcohol is getting turned to haloalkanes, and if it is a 3 degree alcohol, you will be getting instant turbidity, and if it is 2 degree, you will get turbidity after 5 to 10 minutes, and if it is 1 degree, you don't get turbidity. But you should note that stable 1 degree alcohols gives instant turbidity. Like if it is a benzylic or allylic alcohols, then it will be giving instant turbidity. You should note that as well. Next, you have coal-base reaction, which is basically a chemical property of phenol. Phenol is turning to salicylic acid in the reagents NaOH and CO2 and H+. You can see that first phenol, when you are reacting with NaOH, you will be getting phenoxide ion. Then when you are reacting with CO2 in the presence of acid, you will be getting salicylic acid. Note this. And CO2 is the electrophile over here. You'll be getting two products in this. One is ortho and other is para. And you can see that ortho product is major. This is because of the stabilized transition state which occurs, because you can see a 6 members transition state being formed. Because of this, the ortho is more stable. Next, we have Remer-Tiemann reaction, which is also a chemical property of phenol. Phenol is turning to salicylaldehyde. Previously, it was phenol turning to salicylic acid. Here it is turning to salicylaldehyde. The reagent is, the first is CHCl3 and aqueous NaOH. The next is CO2 and acid H plus H2O. First, when phenol is reacted with CHCl3 and aqueous NaOH, you will be getting an intermediate like that. Then further, when you are reacting with NaOH, you will be getting an ion like that. And then finally, when you are treating with acid H plus, you will be getting salicylaldehyde. I hope you got. Next, we have tests for phenol. The first reagent which we will be using is FeCl3. And when you are reacting phenol with FeCl3, we will be getting a purple colored complex like that. And then we have bromine and water. When you are reacting bromine and water in 273 Kelvin, you will be getting a white PPT product, and you can see the product over there. This way, we'll be testing for phenols. Speaking of Williamson ether synthesis, you will have alkyl halide reacting with alkoxide to get a ether. But you should note that alkyl halide here should be less hindered. When this alkoxide is attacking over the alkyl halide, this is following SN2 reaction and it should have less hindrance. And you will get the ether. But if the alkyl halide is more hindered, like 2 degree or 3 degree, it will undergo E2 reaction and elimination occurs when alkene gets formed. For example, you can see below, it is a 3 degree alkyl bromide. And when this is attacking, it does not attack the carbon. Instead, it attacks the hydrogen, and it is acting as a base and it is attacking the hydrogen and it is forming alkene over there. You can also form ether from phenol with one group as aryl group and other as alkyl group. You can see when you are reacting phenol with NaOH, you will be getting that phenoxide moiety, and then when you are reacting with alkyl halide, you will be getting the final ether. I hope you got this. Then we have Dow's process, which is preparation of phenol from chlorobenzene. When you are fusing chlorobenzene with NaOH in drastic conditions like 623 Kelvin and 300 atmospheric pressure, we will be getting phenoxide ion, and then when we are reacting with acid like HCl, we will be getting the final final phenol. And you should note that we are using such a drastic condition over here because the bond between chlorine and benzene has a partial double bond character, and hence the drastic conditions are coming. Moving on, in carbonyl compounds, we have Rosenmund reduction as our first named reaction. This is the preparation of aldehydes from acid chloride, and the reagent is H2 and PD, palladium barium sulfate. This is used as the poison because to avoid further reduction from aldehyde. You can see that benzoyl chloride is getting converted to benzaldehyde over there. Next, we have Stephan reaction, which is the preparation of aldehydes from nitriles. You can see the reagents as SnCl2 and HCl, and the next step it is acid. You can see the nitriles, they are first, when they are reacting with Sn2 plus and HCl, they are forming an imine over there. You can just split this bond and add hydrogen and hydrogen over there, and you will get that. Then when you are reacting with acid, you are getting the aldehyde. Here also you can break this bond and add oxygen over there. Simple. I hope you got this. So nitriles are getting converted to aldehydes. The next is etard reaction, which is preparation of aldehydes from hydrocarbons. And you can see that toluene, when it is reacting with chromyl chloride, you are getting aldehyde. This is the intermediate complex which is getting formed, and I hope you got this reaction. Next, we have Gattermann-Koch reaction, which is also a preparation of aldehydes from hydrocarbons. Here, benzene, when you are reacting with carbon dioxide and HCl, and then in the presence of anhydrous aluminum chloride or copper chloride, you will be getting benzaldehyde, and this follows electrophilic substitution mechanism, and the electrophile is this. We can note that. Next, we have Clemmensen reduction, wherein we are reducing a carbonyl to a hydrocarbon, and Clemmensen reduction we will be using the reagent ZnHg and in the presence of HCl. As this is acidic medium, this reduction fails when an acid sensitive group is present. Next, we have Wolff-Kishner reduction, wherein we are reducing with the help of NH2, NH2, hydrazine, and KOH, which is a base. You can see the reaction over here. First, when we are having a carbonyl group, it is reacting with the hydrazine to form something like this. And then when it is reacting with a base, we are getting the final hydrocarbon over there. And as this is happening in basic condition, this fails when there is a base sensitive group is present. Next, we have few oxidation reactions. First, we have tolerance test, wherein aldehydes are getting oxidized to carboxylate ion, and we can detect the presence of aldehydes. The reagent over here is ammoniacal silver nitrate, and you see that it is forming Ag as precipitate, which gives a silver mirror lining in the test tube, which you can easily find. Next, we have Felling's test, which is also the oxidation of aldehydes to carboxylate ion. You can see the Felling reagent over there. The Felling solution A is freshly prepared copper sulfate, and Felling solution B is sodium potassium tartrate, and you see that there is a red brown PPT getting formed, so you can easily detect this as well. Now, speaking of tolerance versus Fellings and which all compounds give these tests, you see that aliphatic aldehydes give both tolerance and Fellings test, but in case of aromatic aldehydes, they give only tolerance test and they does not give Fellings test. So you can note that. Then in case of ketones and carboxylic acid, they neither give tolerance nor give Fellings test. But speaking of alpha hydroxy ketone and formic acid, they give both tolerance and Fellings test. Now we'll see why. In case of alpha hydroxy ketone, you have a alcoholic group over there which gets converted to a aldehyde. Alpha hydroxy aldehyde, it gets oxidized, and hence it will give the tolerance and Fellings test. And in case of formic acid, you can see that the aldehydic CH bond is present, and so it gives tolerance and Fellings test. I hope you got this concept. Moving on, we have haloform reaction, which is basically a test for methyl ketone group. And the reagent, you can note that it is NaOH plus X2, and sometimes they give you as NaOX. That also you should remember. And when we are taking iodoform, you can see that here you are having a methyl ketone group, and when you are treating with NaOI, you are getting yellow crystalline solid iodoform getting formed. Hence, you can detect the methyl ketone group. Not only methyl ketone, you can see that this alcoholic compound also shows positive haloform test. This is because this alcoholic group is oxidized in the presence of NaOI to the ketone group. So you can see that you are having a methyl ketone over there, and hence it gives positive haloform test. I hope you got this. Next up, we have aldol condensation, and this reaction happens only when there is a presence of alpha hydrogen to the carbonyl compound. Hydrogen attached to the carbon adjacent to the carbonyl group is called the alpha hydrogen, as you can see over here. You should also note that alpha hydrogen is acidic due to a strong withdrawing effect of the carbonyl group over here. Hence, it is more acidic. And this aldol condensation, what happens is the carbonyl having at least one alpha hydrogen will be converted to alpha beta unsaturated carbonyl compound in the presence of the reagents diluted bases like NaOH and aqueous Na2CO3, which releases OH in the presence of water, and barium hydroxide. You can look the mechanism over here. You have the aldehyde over here, and the base is attacking the alpha hydrogen. And when it is attacking, you are getting the enolate ion getting formed. And next step, what happens is the another aldehyde, it is this carbon is electrophilic, and this electron, this oxygen minus is going here, and hence it is attacking the carbon there, and then it is forming the this product. This is addition of enolate ion step. The next step is the formation of aldol. What happens is this O minus is attacking the hydrogen of the water, and it is forming this. You can see in alpha position you have got alcohol, and this compound is called aldol. And then there is a condensation happening. It follows E1CB mechanism. We'll discuss that in some other video. E1CB, what happens is this alcohol in the alpha position and the hydrogen is removed, and you have a alpha beta unsaturated aldehyde. This is alpha and this is beta, and hence you are getting alpha beta unsaturated aldehyde forming over here. I hope you got this mechanism, or else take a pass and you can digest this mechanism, and next we'll be moving on to the next one. But before that, we have a trick to write aldol condensation when there is simple reactants given. You can see there is two aldehydes written over there, and the alpha hydrogen and the carbonyl group, you can see these both form to get alcohol, and this carbon attaches. In the next step, you can see that this carbon and this carbon has attached, and this hydrogen and O is combining to form OH, alcohol, in the presence of dilute NaOH. And next, what happens? You will be, when you are heating this OH and this hydrogen, they combine and get lost as water, and you are having alpha, beta, unsaturated aldehyde getting formed. I hope you got this trick as well. Next, we have cross aldol condensation. When we are having two different carbonyl, at least having one alpha hydrogen, two different aldehydes are present over here, and the reagents are same. NaOH, diluted NaOH, KOH also diluted, and barium hydroxide. Let's take this example wherein you have two different aldehydes and you are reacting with dilute NaOH. You are getting four different products, as you can see over here. The first two will be the self aldol condensation products, and the next two are the cross aldol products. You can see the first one over there, and the second one, you can learn the trick once again. Here you have two carbons, and carbon will be attaching, and the alpha hydrogen of the other aldehyde and the O of the carbonyl groups combines to form alcohol, and you are finding this. Then this alcoholic group and the hydrogen eliminates as water, and finally you are having alpha beta unsaturated aldehyde, same as simple aldol condensation products. And next you have Cannizzaro reaction. This happens when there is aldehydes with no alpha hydrogen, and there are three Cannizzaro reaction. One is simple, cross, and intramolecular. We'll see that. In the simple Cannizzaro reaction, the aldehyde with no alpha hydrogen is getting converted into salt of carboxylic acid and as alcohol. The reagents are sodium hydroxide concentrated. Earlier it was diluted. Here it is concentrated bases, and you will be heating in the next step. And if you are noting here, this is a disproportionation reaction because aldehyde is getting oxidized to carboxylic acid and getting reduced to alcohol. You can note that. You can check out this example wherein we have formaldehyde getting converted to sodium ion of carboxylic acid and alcohol over here in the presence of concentrated NaOH. Now, when it comes to cross Cannizzaro reaction, we have two different aldehydes, and there is a confusion which will undergo oxidation and which will undergo reduction, because we know oxidation and reduction happens. That you have to note that aldehyde which is reactive to nucleophilic addition undergoes oxidation. That is aldehyde which is more electrophile. Aldehyde which is more electrophile and it is wanted to get attacked by the nucleophile. Such an aldehyde will undergo oxidation and other will undergo reduction. You can check out the example over here. You see that here you are having benzaldehyde and here you are having a formaldehyde. And when you are reacting this with concentrated NaOH, you see that as formaldehyde is more electrophilic, it is getting oxidized to a sodium salt of carboxylic acid, and the other one is getting reduced to alcohol, you can see. And CHO, benzaldehyde, is more nucleophilic because of the presence of plus R group. Benzene is plus R, and so this carbon is electron rich. Sorry, it is electron rich, and hence you can understand this. Next, you have intramolecular Cannizzaro reaction. This, when it happens, is when there are dialdehydes or alpha ketoaldehydes, and this also form hydroxycarboxylate. And here also you need a strong base. It is very similar to the Cannizzaro reaction. You can check out over here. Here we are having alpha keto and aldehyde. We can see when concentrated sodium hydroxide is reacted, this ketone is getting converted to alcohol and this aldehyde is getting converted to sodium salt of carboxylic acid. But why? The same concept applies over here also. Which is more electrophilic, it gets oxidized, and which is more nucleophilic, it gets reduced. Here also you can see that this group is plus R group, and this carbon, the alpha carbon over there, is more nucleophilic, and this is more electrophilic. Hence, this is getting oxidized to sodium salt of carboxylic acid and the other one is getting reduced to alcohol. I hope you got this concept. Next, we have benzoin condensation. In this, the aromatic aldehydes in the presence of alcoholic casein, it's converted to benzoin. You can see what is benzoin in the later. Here you see there is a aromatic aldehyde over here, and when in presence of casein, Cn minus is attacking this C and you are forming a compound like this, then there is a interchanging of this charge and hydrogen taking place and you are getting a compound like this. Now, similar to aldol condensation, it's not exactly, but it is kind of similar. You can see that C minus is attacking the carbon of the carbonyl, other aromatic. Here also you need two aromatic aldehydes. Here it is attacking, and you can see this compound is getting formed. Now what happens? This minus and this hydrogen once again undergo interchange. And after it undergoes interchange, you will get a compound like this. And finally, what happens? This minus, this goes like this, and this comes like this, and the elimination of cyanide ion takes place. And you can see this is the benzoin getting formed. So the first step is nucleophilic addition of Cn minus. Here, this is acting as a nucleophile, and carbon over there, as the oxygen is more electronegative, it is pulling the electron towards itself, and carbon is becoming electron deficient. Hence, it is becoming electrophile and it is attacking there. The next step is nucleophilic addition of carbanion. Similarly, this carbon minus, this carbanion is attacking the electron deficient carbon in this compound, and the reaction is happening. And the final step is removal of cyanide. I hope you got this reaction as well. Next, we have Jones reagent. This is the preparation of carboxylic acid from alcohols. When you are having 1 degree alcohol, it gets converted to carboxylic acid, and 2 degree alcohol gets converted to ketone. Note that the reagent is over here, CrO3 and H2SO4, or sometimes it is written as aqueous H2CrO4. And you can see the reactions. 1 degree alcohol is getting converted to carboxylic acid, and 2 degree alcohol is getting converted to ketone. Next, we have HVZ reaction, Hell-Volhard-Zelensky reaction. This is the substitution reaction in hydrocarbon part of the carboxylic acid. You can see that carboxylic acid is getting converted to alpha halo carboxylic acid. You can see this is the carboxylic acid, you can see, and this is the alpha hydrogen, alpha carbon, and this is the alpha hydrogen. This hydrogen is substituted as chlorine, but in which condition? The reagents are X2 in the presence of red phosphorus, and the second step is H2O. X can be chlorine or bromine. You can note this is the reagent X2 in the presence of red phosphorus. I hope you got this reaction as well. Next, before moving to amines, if you haven't watched my physical chemistry and inorganic chemistry one shot, do watch that and get benefited. And if you are enjoying this video, do subscribe and let me know your thoughts in the comments so that I can improve it later. And let's start with Gabriel phthalimide synthesis. And this is the preparation of amines from phthalimide. You get 1 degree amines like this, and the reagents are alcoholic KOH, alkyl halides, and at last you will have water, aqueous NaOH. And only 1 degree amines can be prepared, and aromatic amines cannot be prepared. We will see why in the mechanism. This is an example of reaction. You can check that. In this mechanism, the first step is the attack of alcoholic KOH on this hydrogen. This acidic hydrogen is attacked by the base, and you are getting potassium phthalimide. And the next step is SN2 reaction, and this alkyl halide is attacking this potassium, and this compound is getting formed. And this is SN2, and hence it cannot deal with the bulky groups. Hence, aromatic halides cannot undergo this SN2 reaction. That's why only 1 degree amines are being formed. And you see later this water. You see aqueous NaOH is used, and aqueous means water, and water comes and they surround, and they this Rn and this hydrogen from this water combines to form RnH2, and the rest you can see that it is forming a sodium salt of carboxylic acid, and you are getting 1 degree amine finally. Next, we have Hoffman bromide degradation reaction. This is also preparation of amines. As the name suggests, there is a degradation. This carbonyl group of amide is getting degraded. Hence, you see that there is 1 carbon less in the product side, and the reagent over here is bromine and aqueous NaOH, or bromine and aqueous NaOH. Sometimes it is written as NaOBr and KOBr. You should not get confused with that. As we saw, 1 degree amines is formed with 1 carbon less than the reactant amides. This is an example, and you see that 1 mole of bromine and 4 moles of NaOH is reacting to form this 1 degree amine over there, and Na2CO3 is also formed. Next, we have carbylamine reaction. This is also an isocyanate test, and this is a test for 1 degree amines. Both aliphatic and aromatic 1 degree amines give this test, and they convert to isocyanates in the reagent chloroform and alcoholic KOH, and when you heat it. And this is carbylamine test because isocyanates produce foul smells which we can detect in the reaction. It follows carbene mechanism, and the intermediate is dichlorocarbene. You need not worry much about it, just remember this. And this is the reaction, and you are forming isocyanates. You can see both aliphatic and aniline. Aniline is aromatic, and both these are forming isocyanates, and these have offensive smell. Hence, we can detect it. Moving on, we have Hinsberg test, and this is the Hinsberg reagent. When you are reacting with 1 degree amines, they form the product. 2 degree amines, they form this product, and 3 degree amines, there is no reaction. This is basically a distinguishing test between 1, 2, or 3 degree amines. Now, if you are asking how to distinguish 1 and 2 degree amine, you see that this hydrogen is acidic, but in case of 2 degree again, there is no acidic hydrogen. And hence, when you are reacting with a base, the 2 degree amines are not soluble, but 1 degree amines are soluble in alkali. Hence, you can distinguish between 1, 2, and 3 degree amines. I hope you got this. These days, benzene sulfonyl chloride is replaced by para-toluene sulfonyl chloride. Finally, you have reactions of diazonium salts. We saw this already in haloalkanes and haloarenes preparation, Sandmeyer reaction and Gattermann reaction. In Sandmeyer reaction, benzene diazonium salt, when you are reacting with Cu2X2 or CuCN in the presence of HX and KCN, you are getting haloarenes and this product. And in case of Gatterman reaction, copper powder is used and we are getting haloarene. You should note that yield of Sandmeyer reaction is found to be better than the Gatterman reaction, hence we prefer that. And with that, we conclude this video. I hope it was really beneficial for you for the quick revision of entire named reactions and tests. And if you haven't checked out these videos, do check it out and share your thoughts in the comments, and do subscribe to the channel and share this video to your friends and your juniors who will be writing JEE next year as well. And thank you for watching. Until then, keep learning, keep hustling. Your JEE is very close. All the best for your JEE mains. Thank you.